Okay, let's talk a little bit about decision trees, or CART. CART stands for classification and regression trees. These are among the most simple models, and I think you'll see after we do some explanation here and some of the reading that they're really straightforward and pretty obvious. So I want to make an assumption here. Let's say that we've got a feature set and then we've got some value. And in this case, we're just going to talk about classification, though it also applies to continuous variables. It's a little bit more complicated and we won't get into it. But just assume you've got a tidy data set with a set of features and values or classifiers that you're attempting to predict. So a decision tree is a set of binary breaks starting at something called a root node. So you start at a root node, then you take the entire data set and you split it into two, and you split down into leaf nodes. The algorithm is pretty straightforward. You evaluate all of the features as candidates for each node, right? You figure out which one of them has the lowest cost. I'll explain what that is in a second. And then you split the data accordingly in a binary fashion according to which classification results in the lowest cost associated with a given feature. So the best feature does the split, and then you perform the process all over again. So at each node, you continue to split, and you continue to split, and you continue to split until one of two things happens. Either your cost does not improve, or you run out of data at some predefined threshold. So that's why these things are called trees. As they grow, they can get really large, right? And they can continue to split, sometimes even on the same feature or multiple features, until they get better and better and better. All right, so let's talk just for a second about what cost looks like. So every time you split the data, let's say you have 100 data points to begin with, and you do the split, and maybe there's 45 here, and there's 55 here, and then maybe there's 20 here, and 35 here. You know, the data starts to thin as it gets lower and lower down. What you do is for each of these splits, right, and let's say this split is true and false, right, you have some sort of cost function that's similar to cross entropy or sum of squared error that we've seen before. Or what's common is something called a Gini coefficient. We won't get into that, but it's a default value that you'll see in scikit-learn. And you want to find the split, the point at which you separate the data that results in the lowest cost, right? And the way that you do that is through an iterative, exhaustive search, typically across both the feature set and within each feature. You know, what's the logical split where you can say, once this value is maybe greater than 10, it's false, and when it's, you know, less than 10, it's true. And when you make that statement, that's where you get 45 and 55. And then from 45 points, you do the same thing with whatever the next best feature is, and you continue to iterate until you've grown a large tree. So it's pretty straightforward, right? You just continue to iterate. The data keeps splitting itself. You keep pushing this cost value as low as you possibly can until you get to this point to where you have a logical set of decisions that then you can compare against values, right? So in order to actually perform a classification, you just walk down the tree. You start from the root node, say, does it meet this condition? Does it meet this condition? Does it meet this condition? And then by the time you get to a terminating node, which are what the last nodes are called, you have your prediction. Okay, in the next section, we'll look and see this applied in scikit-learn, and you'll see that it's actually a pretty straightforward process.